In the last lesson, we looked at the basic exponential growth model for bacteria, and in this lesson, what I'd like to do is talk a little bit more about exponential growth. So the first thing we're going to do is fit an exponential model to data. We're going to assume that we have an idealized set of data. So if we were to graph our exponential function, all of our data points would live perfectly on the graph of that function. And what we're going to do is find that exponential model two different ways. So we'll end up with the exact same function both times, but we'll take two different approaches because the second approach is something that might be a little bit easier to work with when our data isn't perfectly idealized. So then we'll talk about how to take exponential data and view it in a different framework so that instead of seeing an exponential shape take place, what we'll actually see is more like a straight line. Okay, we'll talk about that. And then we'll talk about how that new framework allows us to judge when exponential growth is actually happening, because it turns out humans aren't very good at that. Okay, so to start with, suppose we have an exponential model of the form that we've already seen. P of t equals p naught e to the rt, where p naught is like our initial population at time equals 0. R reflects the growth rate. T is the independent variable time, and then P of t is, say, our population over time. Of course, this kind of model doesn't just model bacteria growth. We could also use it for, say, chemical decay. If R was negative, you'd be looking at exponential decay. But anyway, given some data, suppose that we want to find P naught and R. So maybe we have bacteria population at a certain time and then at a different time, and we basically want to fit the model to those 2 points. So we'll do this two different ways. The first way, we're going to stick with the exponential function the way it's written. We're going to plug in and solve for those parameters P naught and R. That's very straightforward. So if you just handed someone this problem on a street, that's probably what they would do. The second way, we're going to take our model, convert it using the natural log function, and ultimately what we're going to do is find the slope and y-intercept of a line. And then we'll exponentiate that to convert it back to an exponential function. So stay tuned for that. Let's stick with method 1 for now. Okay, so here's our problem. You are told that after 2 days, so when time equals 2, a bacteria population is about 623. So in other words, P of 2 is 623. 3 days later, I have to be careful there, that's not t equals 3, that's rather t equals 2 plus 3. So 3 days later is like t equals 5. The population is about 769. So P of 5 is about 769. What was the starting population? In other words, what's that parameter, P naught? And what is the growth parameter, R? Then we can also determine the doubling time. So R is like a growth parameter, but that's not exactly the doubling time, but from that we can figure out the doubling time. Okay, let's solve this problem by plugging this pair of values that we have into our exponential. So we have two equations. The first one is going to be 623, that's P of 2, equals the unknown starting population, e to the unknown growth rate times 2. So t equals 2. The second equation is 769 equals the same unknown starting population, e to the r times 5. Now you have some options here for how you would like to proceed. The way I've written this makes me just think of division. If I divide the left-hand side of the first equation by the left-hand side of the second equation and the right-hand side of the first equation by the right-hand side of the second equation, the p naughts will actually cancel out. Normally when I write mathematics, I just go down the page, but with these slides, since my pages are wide rather than tall, sometimes I write over to the right, but that's not normally what I would like to do in my own personal notes, but let me just write it over there. So if I divide line 1 by line 2, on the left-hand side we'll have 623 divided by 769. And on the right-hand side we'll have, let me first just write the entire thing, so the starting population e to the 2r divided by the starting population e to the 5r. And then the reason we did this is the starting populations canceled out, leaving us with just one unknown. And I can simplify that right-hand side as e to the 2r minus 5r. In other words, negative 3r. Let's take the natural log of both sides. That will undo the exponentiation, if you will, on the right-hand side. So natural log of 623 divided by 769 is natural log of e to the negative 3r, but of course that's just negative 3r. So then we get r is natural log of 623 divided by 769 divided by negative 3. You could take those natural logs if you want to and separate them. So you could write natural log of 623 minus natural log of 769 divided by negative 3. You can multiply the top and bottom by negative if you'd like to. I would keep this expression handy. You know, if you're working in a calculator, Excel, or MATLAB or something like that, you might want to have this true expression for r rather than using the approximate form, just to make future calculations a little bit closer to being correct. But if we go ahead and crunch that, we would get r is about 0.0702. Okay, so that's our growth rate. To find the starting population now, I just need to use, say, the first equation. So I can plug in for r, and if I were doing this in a calculator, I would plug in the entire closed form expression. Then take that, divide it over, and solve for p0. So let's do that. So given r, the starting population is going to be exactly 623 divided by e to the 2r. And then if I actually now evaluate that, that's about 541. So there's rounding in this problem, and that's okay. So I rounded to the nearest whole number because we're talking about a starting population. So that seemed like a sensible thing to do. Now for the doubling time, you may have picked up on a formula last time that you can always use, but let's rederive it just in case you didn't see it. So what is the doubling time? For this, I would not use the expression for p0 that we just found. There's no reason to plug in 541 because actually we're going to cancel out our p0s. So we're interested in when the starting population doubles. So let's put 2 p0 on the left-hand side and then just p0 on the right-hand side and then e to the rt, where r is, let's say, the closed form expression if I'm working in some software or something like that. And then again, there was no reason to put in 541 because we're going to cancel those out. We have, of course, now 2 equals e to the rt. If you take the natural log of both sides, you get natural log of 2 equals rt. So the doubling time, and actually let me call this t star, just to kind of indicate that we're solving for a special moment. T star in an exponential model always satisfies natural log of 2 divided by r. So that was the formula you may have spotted in the last lecture. And then in this particular problem, that's about 9.9 days. Okay, so what is our exponential model? Well, it's p of t. If we wanted to write it out and plug in everything, that would be 541 e. And then let me write, how about 0.0702t? Of course, that's an approximation. So just by plugging 2 known points into our exponential model, we were able to find this as our exponential equation. Now what we're going to do is we're going to rederive this exact formula. So we're going to solve the exact same problem. We'll get the exact same answer, but our technique will be a little bit different.
Okay, so let's look at our second approach. So consider the following. Let's take our exponential function, P of t equals p naught e to the RT. And let's take the natural log of both sides. So on the left-hand side, we'll just have natural log of P of t. And then for the right-hand side, we'll have natural log of P naught e to the RT, of course. But the natural log of a product can be separated into a sum of natural logs. So that's going to be natural log of P naught plus natural log of e to the RT. And then, of course, natural log of e to the RT is just RT. So I'm going to rewrite that right-hand side in its most simple form. Just to make it clear what we're looking at, let me take t and replace it with x, and natural log of p of t and replace that with y. Then we have y equals, and I'll shuffle the terms on the right-hand side, rx plus natural log of p naught. R is a number, natural log of p naught is a number, so what we're looking at is the equation of a line. We'll go back to using the form just above with natural log of p of t on the left-hand side, but I just wanted to see this line really take shape. So now what we'll do is plug our two known points into the equation of the line, solve for r in the initial population that way, and then we'll convert our line back into an exponential function. So for our first known pair of values, when time equals 2, the population was 623. So I'm going to plug 623 in for p of t and 2 in for t on the right-hand side. So we have natural log of 623 equals, how about 2r plus natural log of the initial population. And similarly, for our second pair of known values, we have natural log of 769 equals 5r plus natural log of the initial population. Now instead of dividing, let me subtract the second equation from the first. That will cancel out the initial population. And just like before, we'll get natural log of 623 minus natural log of 769 is negative 3r. So just like before, r is the left-hand side divided by negative 3. Now we can just plug that into the first equation and get that natural log of the initial population is natural log of 623 minus 2r. Let's go ahead and exponentiate both sides. So if I do e to the left-hand side equals e to the right-hand side, on the left-hand side, we're left with the initial population. And on the right-hand side, if you crunch those numbers, you get the same thing as before. It's going to be approximately 541. Okay, so we have the same expressions as before. Normally in math, you don't want to solve every single problem two different ways just to get the same answer twice. I would say that neither of these was really more work than the other. The first method might have felt a little bit more natural. With the second method, we took a detour to rewrite our equation in a form that looked like a line. So a follow-up question is, when might the second method be preferable? If it wasn't computationally simpler than the first method, and in some ways it was conceptually more difficult, why would we ever want to do that? And here's something I would like for you to consider. Suppose from day equals 0 to day equals 10, I've generated this collection of data. It looks exponential. We'll actually talk a little bit about when do things really look exponential in a few minutes, but let's just look at this and say that probably there's an exponential function that would be a good model for this data. However, while I was careful when recording my data, I wasn't perfect. So this data isn't going to fit perfectly on the graph of any exponential function. So how do we fit an exponential function to this data? But let's say we tried to find an exponential model that would pass through all these data points. Well, we only have 2 unknown parameters, so we would want 2 data points if we were going to do this by hand. Which 2 do you pick? If you start with the first 2, and solve for it, I've actually done this for you here, you see that it's not a very good model. So this exponential curve here perfectly passes through the first 2 points, and then it gets kind of off course. Okay, so then what I did was I picked the first point and the third point, and I got a little bit better, but it's still not a very convincing fit. Now I could keep trying different pairs, or maybe I have a device, like a certain type of calculator or numerical software, that will do this job for me. But here's a different approach that's going to reinterpret this question not as trying to find an exponential function of best fit, but find a line of best fit. So instead of plotting y versus x, let's plot natural log of y versus x. So what you're looking at here on the left is our original collection of data, what we were trying to fit an exponential curve to. And on the right, the x values are the same, but I've taken the natural log of the y-axis. So if this is roughly exponential, when you take the natural log of the outputs, you get roughly a line. So instead of relying on a piece of technology to find an exponential of best fit, which I might not be able to do with every piece of equipment, I think I'm more likely to be able to find a line of best fit. Or at the very least, I might be able to eyeball, perhaps with a ruler or something like that, which 2 points I would like to use if I needed to manually generate a line of best fit and I didn't have the algorithm or the equipment to do that exactly. Okay, so if we just focus on that picture on the right, we have the same inputs as before, but now we've taken the natural log of the outputs. I've plotted this in MATLAB, and then what I said was, MATLAB, generate my line of best fit. So MATLAB created this line for me. It uses the least squares technique for finding a line of best fit. A line is a pretty simple object though. So if I didn't have the least squares algorithm available or the technology available to create a line of best fit for data which doesn't live perfectly on a line, I might be able to eyeball, like use the first one and that one and fit the line through those points or something like that. It just might be a little bit faster than trying to figure out which points to use for the exponential function. Okay, so here's our line down here. Now we can take this line and turn it into an exponential, and here's how we do that. What we have is natural log of y equals 0.30048x, of course that's approximate, that is rounded, plus 2.9681. Exponentiate both sides so that on the left-hand side we'll just be left with y. We'll have y equals, and then on the right-hand side we have e to the 0.30048x plus 2.9681, but I'm going to break that apart into the product of two exponentials. So that's going to be e to the 0.30048x e 2.9681. That first term looks like e to the rx or e to the rt. I've switched letters here. And then the second term is just a constant. That's actually what we would think of as our initial population. So from the slope and y-intercept of my line of best fit, I'm able to find the initial population and the growth rate. I now have the exponential function. I manually graphed that. So with those numbers, I was able to write this curve for my exponential model. And now you can see it's a much better fit than what I started out with. Another nice benefit of recasting an exponential problem into that of a line is that if you had to just make a quick judgment call, I think we're better at interpreting lines than exponential functions. In particular, the slope, I can eyeball a slope a lot more easily than I can eyeball a growth rate when looking at an exponential curve. So even if you didn't get the exact line of best fit, you could come up with some approximate numbers just based on your comfort level with lines. In general, and I think the COVID-19 pandemic has really magnified this for me, I think that people do not have the ability to intuitively feel exponential growth like they feel linear growth. I've seen people say, oh, yesterday the number was 500, today the number is 2000, that's exponential growth. And that's not exponential growth if you just have two values, right? Through two values, 2 points on the plane, you don't know what shape you should draw. Could be a line, could be an exponential curve, could be sinusoidal. With just 2 pairs of values, you can't judge what the growth is really like. So listening to people talk about exponential growth, this, that, I think what they're really trying to say is explosive growth. So let's consider these 3 pictures. I designed these pictures in MATLAB. I just created functions and made these bar graphs and also kind of like a curve connecting the top of the bar graphs. I made them to try to look like the types of coronavirus data that I've been looking at all year. And my question is, which of these looks like exponential growth? And I think that for an average human, particularly if you just gave them one of the pictures, like if you handed them just this picture on the left and said, does that look like exponential growth? I think most people would eyeball it and say, yes, that's exponential. Look how it's going up so steeply. And same for the middle and the picture on the right. I think it's hard for a person to look at a graph and judge exponential growth just by the shape of it. So let's come up with a test for when what you're looking at is actually exponential growth. And this test is actually done on a lot of the websites where people find COVID-19 data. So for example, I've looked at CDC data from North Carolina. I've also looked at this website that's pretty popular called Worldometers. They have a lot of data there. And what you sometimes see with charts showing cases per day or hospitalizations or something like that is you see an option to switch from this kind of viewpoint, where it's y versus x, to a log y viewpoint. So if these were actual charts that you would see on one of those websites, there might be a button that says show the logarithmic data. And what they do is they leave the independent axis the same. So x is the same on the top row and the bottom row. But then they take the log of the outputs. Say this is number of cases per day. They take the logarithm of that and plot it. And the reason why you would like to look at data that way is because it's much easier to eyeball true exponential growth on a log plot than on a regular plot. And that's because exponential growth on a log plot, as we saw a minute ago, should look like a straight line. The steepness of the line isn't so important. So if this was really steep, that would be fastly growing with a high growth rate. If it's just barely steep, kind of like in this example, it might be a lower growth rate. But overall, this is exponential growth because it's a linear looking pattern of growth in the log plot. So if we go back to our demonstration, if we looked at the log plot for this first set of sample data, while eyeballing the sample data might have made you think, hey, that's exponential, because look how fast it's growing. In the log plot, it's clear that this is not a straight line. So this is not exponential growth on the left. It's roughly quadratic. I made this data in MATLAB, so it's basically a quadratic function. And then when I took the logarithm of it, you can see it's not growing at an exponential rate. It's sub-exponential because it's concave down like a frown. So if you see your data kind of flattening out like this, that means it's not as fast as exponential. Now, this middle set of data is actually exponential, or close to exponential. What I did was I created these data sets and then I added in a little bit of noise so that they wouldn't be perfectly resembling one function or another. But if this was, say, cases per day, and you took the log of that data, so you were looking at the log plot, if you saw this, that would tell you exponential growth. Because again, while there's a little bit of noise so that it's not a perfect line, when I took the log of, say, this black line on the top graph, it's really close. So looking at this, you would say, wow, that's exponential growth. Now let's look at what's happening with this picture on the right. Actually looks really slow for a while and then it explodes. When you take this black curve and you take the log of all of its y values and do that plot down here, notice this is slightly concave up like a cup. That means it's increasing at an increasing rate, so it's getting steeper and steeper. When you see that, it's really worrisome if you're looking at something like COVID-19 cases per day, because that means it's actually growing faster than an exponential function. You could think of this as like sub-exponential, exponential, and super-exponential. So I like this test. I like when I look at these graphs and I switch over to a log plot because it's hard to eyeball exponential growth, but it's easy to eyeball a straight line. So that's the motivation behind doing a log plot whenever you're investigating whether exponential growth is occurring. It's easier to gauge how truly exponential it is when you plot the log of y versus x. Okay, so I hope you enjoyed this deeper look at exponential growth. Thank you for your attention.